Hello and welcome back to the Biochemistry for Health Sciences channel. So in this video, we are going to start talking about carbohydrates. And first thing we're going to do is go through some definitions. Carbohydrate chemistry has a lot of definitions that is medically relevant. It's important to understand these chemical concepts so that you can understand reading medical journal articles about carbohydrates, as well as understanding some of the clinical lab tests that are used that are related to carbohydrates. So one of the carbohydrates that we really focus in the clinical world is glucose, which is also called in the clinical setting by an older name, dextrose. So here's the structure of glucose. In organic chemistry, as you know, we had talked about functional groups. So this is the aldehyde functional group. So if any sugar has an aldehyde functional group, then we call that sugar an aldose. So just for comparison, here's another sugar, fructose. You can see fructose has the ketone group. Therefore, fructose is a ketose. Now, the number of carbons, so you can see there's 1, 2, 3, 4, 5, 6. So if the sugar has 6 carbons, then we use the prefix hexa and end it with an OSE for sugar. So this is an hexose. Similarly, fructose has 6. So fructose is also a hexose. We can combine these two and that will give you an aldohexose. Okay, or in this case, a ketohexose. Okay, so 6 for hexose. Suppose there were 5 carbons, then you can call it a pentose. Okay, if there were 4 carbons, you can call it a tetrose. The sugar would be a tetrose. 3 carbons will be a triose. Okay, and so on. Okay, so you can see you can have, again, you can have pentose, aldopentose, or ketopentose, or aldotetrose or aldotriose, and so on by combining these two words. The carbohydrates we find in our body are certain isomer and enzymes that carry out the metabolism for these chemicals in our body. They can actually recognize the isomers. Okay, so in this case, the D isomer is the carbohydrates that we see most often in our body. Okay, so here the hydroxyl group is drawn on the right-hand side. This is the hydroxyl group furthest away from the functional group aldehyde. Similarly, this hydroxyl group is the furthest away from that functional group ketone. And so this hydroxyl group is drawn on the right-hand side, we call that the D isomer. If the hydroxyl group is drawn on the left-hand side, then that will be an L isomer. Okay, so some of the definitions for glucose. Now, how does glucose exist in serum or in water in general? Well, this is a very interesting and very, very important concept to understand because this relates to diseases such as diabetes. So there's a very important reaction that can happen even in water very well. And that is a reaction between an aldehyde or ketone and a hydroxyl group. And the product is called a hemiacetal. Basically, it's a chemical where there is a carbon. To this carbon is attached an OH group as well as a OR. And let's look at this by looking at what happens to glucose. So here's the one form of glucose, the non-cyclic form. And you can see the aldehyde group is here. And there are so many hydroxyl groups. Okay, remember reaction between aldehyde and hydroxyl. So there are so many hydroxyl groups. So basically any of these hydroxyl groups can react with this aldehyde. Okay, any of these. But the most stable structure is obtained when this aldehyde and carbon number 5, reacts with this. When this hydroxyl reacts with this aldehyde. Okay, and then what you see is these two joining together, 5 joining 1. Okay, so this is 1, 2, 3, carbon 4, carbon 5. So 5 joining 1 through an oxygen. You see, and that forms a cyclic structure. Cyclic structure. Okay, so the non-cyclic form has been converted to a cyclic form. So before the reaction, the carbon 1 was a aldehyde carbon, but now carbon 1 has become, you can see there's a hydroxyl group. So this carbon 1 has a hydroxyl group and an OR. R just means the rest of any other carbon. Okay, so R here just means any other carbon. Okay, so now this carbon here has a OH, you see, has an OH and an OR. So OR, OH. So this is a hemiacetal carbon. Okay, that's a hemiacetal carbon. Now notice that this new OH group, so this is a new OH group, can be found either above the plane of the ring or it can be found below the plane of the ring. Okay, because this is a new OH group, the product can have OH either above the plane or below the plane. We usually use this as a reference point. So in this case, both the groups are above the plane and we call this beta glucose. Okay, we use carbon 1 and this is carbon 6. Okay, so the carbon 1 and 6 are on the same side, we call it beta. If carbon 1 and 6 are on the opposite sides, so carbon 1 is here, carbon 6 is here, opposite sides, then we call it alpha. Okay, so there are 2 forms of the cyclic structures of glucose, the beta form and the alpha form. So the non-cyclic glucose in water can form beta glucose cyclic, alpha cyclic glucose. These 2 cyclic forms are the major forms in your blood, in your serum. More than 99.9% of glucose is cyclic. Very little, less than 1%, much less than 1% is the non-cyclic form. Now remember, this arrow means reversible. Okay, this is a reversible reaction, reversible. That means this cyclic, this joining here between this and this can open up to give you back this. Okay, so this can open up to give you back this. So you can get back, the cyclic form can become converted back to the non-cyclic form. And once again, you get the aldehyde. So this can happen. Okay, so this can happen. But under cellular conditions, under physiological conditions, these 2 are the more stable forms. This is only 1% or less. Another definition that we come across in clinical journals, articles, and lab tests is this definition of a pyranose. So what do you mean by glucose is a pyranose? Well, pyranose, there's a chemical, organic chemical called pyranose. It looks like pyranose. So pyranose has 1, 2, 3, 4, 5, 6. So if the sugar has 6 sides, then it's a pyranose. So glucose has 6 sides. That's the most stable form of glucose. It's a pyranose. For comparison, here is fructose. Fructose has 1, 2, 3, 4, 5 sides. So fructose is a furanose. So basically any sugar that you see that has 5 sides in the cyclic structure is a furanose, 6 sides is a pyranose. Another very important clinical definition is the reducing sugar. Very often articles will talk about reducing sugar. So glucose is a reducing sugar. What do you mean by that? So you can see any chemical that is an aldehyde or ketone, or that can break open and give you back the aldehyde or ketone, in this case the hemiacetal. This is your hemiacetal, because remember that's a reversible reaction. So any chemical that have aldehydes, ketones, or in this case also the hemiacetal, these are all reducing sugars. Okay, they are reducing sugars. That's because aldehydes and ketones are reducing chemicals. And we'll look at the clinical use of this in a few seconds. Okay, so these are reducing sugars. Here's another sugar, lactose. Lactose, you can see lactose is made up of galactose joined to glucose. Okay, so if you look at this part here, you don't see any aldehyde or ketone, but if you look at this carbon, this is an OR and an OH, so this is a hemiacetal. Because there's a hemiacetal present, lactose is a reducing sugar, right? Because there's a hemiacetal. This hemiacetal can open up to give you the aldehyde. Okay, so lactose is a disaccharide. That means there are two sugars joined together. Lactose is a disaccharide, and it's a reducing sugar. Let's look at the sugar that we always call sugar in everyday life, and that's sucrose. Okay, so sucrose, this is the structure of sucrose. You can see in the structure of sucrose, there is no aldehyde, there is no ketone, there is no hemiacetal. Okay, so if you look at this carbon here, this has OR and OR. Okay, that's not a hemiacetal, we actually call that an acetal. Okay, any carbon that has two ORs, that's an acetal. So same thing here, this carbon has an OR and an OR, that's an acetal. So this carbon is an acetal here, but this is a hemiacetal. So lactose is a reducing sugar, but sucrose is not, because if you look at anywhere here, you don't see, so let me erase this, you don't see a hemiacetal. So this is not a hemiacetal, it's an acetal. Similarly, this is not a hemiacetal, it's an acetal. Why? OR. Okay, so there is no hemiacetal or aldehyde or ketone in sucrose. So sucrose is not a reducing sugar. Okay, so that's how we differentiate what's a reducing or non-reducing sugar. So reducing sugars are sugars that have aldehydes, ketones, or groups that can open up to give you aldehydes or ketones, such as the hemiacetal. Acetal cannot open up. Acetal reactions are irreversible. Okay, acetals do not open up to give you back the non-cyclic form. There is a test for reducing sugar that we do in urine, and this test is typically done to screen inborn errors of metabolism, genetic diseases such as galactosemia, where the galactose is not metabolized by the baby and it comes out into the urine. So usually if the glucose test is negative in the urine, glucose is also a reducing sugar, and so is galactose. So if glucose is negative, but the reducing sugar test is positive, that means there's something present in the urine that is causing the reducing action. And the test is actually very simple and very cheap. Any reducing agent, anything that's reducing, so for example, glucose is reducing sugar, it will react with copper 2+, the cupric ion, which is blue in color. You can see it's blue in color. And when that reaction happens, you get red cuprous from Cu+. So basically the blue color changes to red, and that tells you, there is something reducing, some reducing chemical, maybe a sugar, maybe something else. Vitamin C can do that too. Okay, so vitamin C, so something reducing. And once there is something reducing, then we can run more specific tests to see is there really a genetic problem with the child. This concept of reducing is also important to recognize larger sugars. We have what we call reducing and non-reducing ends. So that's an important definition that you have to also look at and understand. So if you look at this structure here, this disaccharide, this is maltose, another disaccharide. You can see this carbon here is an OROH, so that's a hemiacetal which can open up. So this part is reducing, but this cyclic structure has no aldehyde, ketone or hemiacetal. So this part is non-reducing. So this is called the reducing end, this end is called a non-reducing end. Okay, because remember this is a OR, that's an acetal. So this is non-reducing. This ring cannot open up. This ring can. Okay, so as we get towards more complex structures of carbohydrates, you can see the two ends are actually different. So when we join glucose together, you get glycogen. And then this is a structure of glycogen. So glycogen, you can see, has glucose joined together, and once in a while there's a branch coming out. Okay, so basically you can see glucose join. Okay, and suddenly a branch coming out, and you get another branch, and then continue joining, and so on. You can see branches coming out, joining alpha 1, 4, and then branch, joining. Okay, so if you look at the structure of glycogen, there is a reducing end, but there are many non-reducing ends. Okay, many non-reducing ends. Okay, so this is very important for glycogen metabolism, because the enzymes, so an enzyme they recognize a non-reducing end. So an enzyme can come and sit here and work on this glycogen. Another enzyme can come and sit here and work on this glycogen, and so on. Okay, and that's very important, because glycogen, we'll see in a few seconds, in the next video, glycogen is how we store glucose. Okay, and blood glucose is so critical for our survival that maintaining blood glucose is very important. Okay, so understanding reducing ends and non-reducing ends it's important to understand glycogen metabolism. Okay, so that's a few important definitions, chemistry definitions. We have to know about carbohydrates so that we can appreciate the clinical significance of carbohydrates in future videos.